Hello everyone and welcome to Lesson 1 Technologies and Smart Grid Integration as a part of the Smart Microgrid and System Integration course of the training program supported by CISA project. My name is Ander Zubiria and I am researcher at the Power System Units of Technalia Research and Innovation. This course has been prepared alongside with my partner Amaya González Garrido. So in this video you will learn about the key technologies for smart microgrid integration into the power system. In particular, we will focus on energy metering and control devices, as well as on the key functionalities for safe and efficient microgrid operation. Here you will find the specific contents of this course. In this picture we can see the main smart microgrid energy resources and assets. So on the left side we can see the generation facilities which are in charge of supplying energy to the connected loads to the microgrid. This can be divided into two main categories: non-renewable sources like gas microturbines or diesel generators, and renewable sources like PV panels or wind turbines. Additionally, we can find energy storage devices which are essential to improve the performance of the microgrid and also to provide backup energy and other services to the microgrid and the whole system, like frequency or voltage support. Then on the right we can see the consumption loads, which are basically the consuming devices connected to the microgrid, which can be, for instance, household lighting systems or productive devices like irrigation systems. These loads can be additionally divided into different categories, as you can see in the picture. Last but not least, we can find the distribution network, which is the group of grid infrastructure and assets where the microgrid is connected. Then, on the core of all this, we can find the main controller or the microgrid controller, which is in charge of managing and controlling the energy and information flows coming and to the microgrid and going to the power system. There are two main types of microgrids according to their connection to the power system. So we can find isolated or off-grid microgrids which have no connection to the wider power system, so they rely totally on the internal energy resources. And then we can find the non-isolated or on-grid microgrids, which do have a connection to the power system, and therefore these act as a controllable unit for the whole power system. Among these last ones, we can differentiate two main operation modes. So these microgrids can operate in a grid-connected mode. So in this case, the main objective of the microgrid would be to optimize the dispatch of all the energy resources, ensuring the energy balance among all local resources, and also ensuring the synchronization with the main grid, so providing appropriate frequency and voltage output from the microgrid. If we jump into the islanded mode, in this case the essential objective would be different, so it would be the stability and the dispatch optimization in a shorter term. So the internal electronical converters or electronical devices would be in charge of maintaining voltage and frequency of the microgrid. Additionally, there's a higher level control, which would be the secondary control that aims to restore voltage and frequency to the referent values to maintain power quality and balance within the system. So in this picture we can see the main modules that build up the microgrid controller, and these modules will be further detailed in the upcoming slides. Here indicated in blue color, the microgrid schedule module is in charge of optimizing the energy dispatch of the microgrid in different time horizons, so ranging from the design and planning phase to the real-time operation of the microgrid. So there are three main tasks of this schedule module. One of these is the microgrid planning, which aims to minimize the investment and operation related costs, optimally sizing and locating the energy resources. Then we can find the unit commitment function, which aim is to minimize fuel and startup costs of fuel-based resources. And then we have the long-term bilateral power purchase agreement management, or PPA management function, which ensures a stable energy price for the renewable energy sources and the microgrid consumers. In a shorter term schedule module, we can find the energy dispatch function, which aims for efficient allocation of power demand and supply. So this is usually done in the day ahead of horizon with different time intervals, for instance hourly, and following different objectives, for instance cost minimization or environmental objectives. And then we can find in a closer to real-time operation framework the market trading functionality, which aims to optimally manage the imported and exported energy from the microgrid respect to the wholesale or ancillary service market. A key functionality for an optimal energy management on microgrids is to forecast generation, demand, and energy prices. This is performed, as you can see in yellow, by the forecast module, which is fed by load generation and price prediction. These predictions are based on historical data, technological features, and environmental and user behavior information. So all this information is then matched, and it provides a tool for decision-making process in order to execute the real-time or day-ahead dispatch of the energy resources. Advanced grid monitoring functionalities enable higher grid observability, end-user metering, fast diagnosis, and advanced functionalities to control and manage the distribution grids. So for that, there are some key devices like smart sensors and advanced metering infrastructure. Smart sensors have advanced functionalities compared to analog sensors and provide real-time data bidirectionally and the necessary grid status information for real-time monitoring, protection, and control. Then the advanced metering infrastructure is a new metering technology which has a very high-speed two-way communication between smart meters and the utility. Islanding detection and protection is a key functionality for advanced microgrid power control. So under islanding operation, the uninterrupted power supply system feeds the microgrid loads. This islanding detection capability can help to detect and limit fault propagation. Many times unplanned islanding situation happens, so this can hamper the power stability, quality, and can modify the protection requirements. Some ways to detect these unplanned islanding situations can be to monitor the rate of change of frequency, the voltage fluctuations, and the phase changes. Power quality monitoring helps to avoid unacceptable disturbances for the microgrid and the rest of the network users. For that, power quality parameters are monitored. For instance, power factor, harmonic data, and also threshold crossing. Some power quality techniques can help to improve voltage fluctuations, harmonic distortions, and also voltage flicker and other problems that may appear in the microgrid. Microgrid protections are fundamental in order to preserve a safe and efficient operation of the microgrid. So in this case, typical protections could be relays that compare measured data against some predetermined threshold values, and when exceeded, this send a trip signal to the breakers in order to avoid further problems. Some protections commonly used could be voltage-based protection, but also overcurrent, differential, or distance-based protections. So here you may find some additional references for further research on the presented topics. So this is the end of lesson 1 on a Smart Microgrid and System Integration course. Many thanks for your attention. Bye.